Hello everyone, today I will introduce the least norm problem in the book of convex optimization. And my speech today will divide it into three parts. In the first part, an example is given to illustrate the definition of the least norm problem. And in the second part, I will introduce some interesting interpretations of this problem. And the third part is the solution of the least norm problem. Let's get on to the first part. Consider a model of a unit mass with zero position and zero velocity at t equals to 0. And now a force Ft equals to xi is applied on this mass. At each time slot, F remains the same. And if we use y1 denotes the velocity, denotes the final velocity of the mass, and y2 as the final position of the mass, then by Newton's law we can get the expression of y1 and y2 like this. If I write y1 and y2 of this form, then we can have y equals to ax. Now we suppose the final velocity of the mass is 0 and the final position is 1. Then since the number of the equations is less than the number of the unknowns, then we will have a lot of solutions to this problem. And now our problem is to find the minimum force. If we use the norm to measure the force, then we can transform the problem into like this. Which is to minimize the norm of x subject to ax equals to y. And this is exactly what least norm problem deals with. Now with the understanding of this example, let's move to the definition of the least norm problem. The basic least norm problem has the form of to minimize the norm of x subject to ax equals to b. And here, A is in R to M by N, and B is in R to M, X is in R to M. Since the objective function and the constraints are all convex, then so this problem is a convex optimization problem. And to make this problem feasible, we should guarantee that M is less equal than N. But since when m equals to n, we will have only one solution, which is x equals to a inverse b. So we are pretty interested at the situation when m is less than n. Next, let's move to some interesting interpretations of the least norm problem. And the first interpretation I want to explain is the control and design interpretation. And the example we just talked about is exactly this control and design interpretation of this problem. Let's look at this problem again. So x here is our control input, which is to be designed, and y is the terminal value of our system. And we require that ax is equals to y. And the least norm problem is a problem to find the minimum value of this control input. And the second interpretation is the estimation interpretation. And let's look at this. If x is a vector of parameters to be estimated, and here we have some perfect linear measurements, which is ax equals to b. And since the measurements since the measurement is less than the number of parameters, which means that our measurements cannot completely determine our parameters. Without any further measurements, we must use prior information. Suppose that our prior information is to ensure that x is as small as possible, and which is measured by the norm. So the least norm problem can help us to choose the one that is smallest. And the last interpretation is the geometric interpretation. And we can see that the feasible set is affine, and our objective function can be understood as the distance between x and the origin. Then the least norm problem help us to find the minimum distance from x to the origin. And okay, so next let's come to the solution of the least norm problem. To be simplicity, here we only consider the norm is L2 norm, and so we can rewrite the problem as to minimize x transpose x subject to ax equals to b. And here, with the problem given, we can construct the Lagrangian function as L equals to x transpose x plus lambda transpose ax minus b. And then we take the derivative of the Lagrangian function with respect to x. Then we get 2x plus a transpose lambda. And we write this derivative equals to 0. We can have an expression of x, which is x equals to minus a transpose lambda over 2. Then we substitute x into the Lagrangian function. Then we get so that we can get the infimum of the Lagrangian function, and which is equals to the dual function. And the dual function is given by and then we can find lambda star to maximize the d lambda, which is equal to minus 2a times a transpose inverse b. And finally, we can, if we substitute the lambda star to x here, then we can get the minimizer of this problem, which is equals to a transpose inverse b. So x star is the minimizer of this norm problem. Okay, so that's how.